Imagine a universe that isn't silent or empty, but quietly active in ways we are only just starting to detect. A reality where light is not merely something that travels between stars, but something that can carry subtle patterns, structure, and possibly deeper meaning. For generations, humans have stared into the night sky asking whether we are alone. Today, that question is no longer limited to imagination. It is being explored with real data and precision. One of the most fascinating places in this search lies just over 4 light-years away, in the Proxima Centauri system. Orbiting this nearby red dwarf star is a planet known as Proxima b, positioned within what scientists call the habitable zone. This is the region where temperatures might allow liquid water to exist, depending on atmospheric conditions. Because of this, Proxima b has become one of the most intensely studied exoplanets. Recent observations in the infrared spectrum have introduced a new layer of curiosity. Subtle variations in heat and light coming from the planet's night side appear more organized than expected. Instead of random fluctuations, the signals seem to follow repeating patterns with relatively stable intensity. This is unusual because most natural processes, such as storms, volcanic activity, or auroras, tend to produce irregular and chaotic signals influenced by constantly changing conditions. What makes this particularly interesting is not a single anomaly, but consistency over time. When a signal repeats in a structured way, scientists begin to question whether it can be explained purely by natural mechanisms or whether something more complex might be involved. That question does not imply a conclusion, but it does open new areas of investigation. The star itself adds another layer of complexity. Proxima Centauri is a red dwarf, smaller and cooler than our Sun, yet far more unpredictable. It frequently releases powerful flares capable of stripping atmospheres from nearby planets. Under such harsh conditions, sustaining life would be extremely challenging. However, if Proxima b has a strong magnetic field or a thick atmosphere, it might be able to retain stability over long periods, leaving open the possibility, however small, of habitable conditions. Scientists are also examining the planet's atmosphere by studying how starlight interacts with it. As light passes through atmospheric layers, it carries chemical signatures that can be analyzed from Earth. Early data suggests unusual combinations of gases, including methane levels that are difficult to explain through standard geological processes alone. On Earth, methane is often associated with biological activity, but it can also arise from non-living sources. This makes it intriguing, but far from definitive. The idea of artificial light sometimes enters these discussions, though it remains highly speculative. If a planet like Proxima b is tidally locked, meaning one side always faces its star while the other remains in darkness, then the night side could, in theory, develop conditions where artificial illumination might exist. If such illumination were present and large-scale, it could produce faint but structured signals detectable across interstellar distances. This remains a hypothesis, not evidence, but it is one that scientists can test by looking for consistent, non-random patterns. There are also more conventional explanations. Reflective ice, shifting cloud formations, or complex atmospheric reactions could create repeating signals under certain conditions. The intense radiation from the star might also drive interactions that are not yet fully understood, producing patterns that mimic organized behavior without requiring any form of technology. To investigate these possibilities, astronomers rely on advanced instruments capable of detecting extremely faint signals. Infrared observations allow them to map temperature changes, identify chemical compositions, and track variations over time. These tools do not directly reveal life, but they help narrow the search by identifying environments where life might be possible. Future technology is expected to push these capabilities even further. New space telescopes and ground-based observatories will improve resolution, making it possible to study distant planets in greater detail. Some concepts even involve blocking out starlight to directly observe planets, which could reveal surface features or more precise atmospheric data. Despite all this progress, caution is essential. Astronomy has encountered mysterious signals before that later turned out to have natural explanations. Objects once thought to be artificial have eventually been explained through physics. This history reinforces an important principle: unusual observations require strong evidence before extraordinary conclusions can be made. Even so, investigating these signals is valuable. Whether they turn out to be natural phenomena or something entirely unexpected, they expand our understanding of how planets behave and how we detect them. Each new observation challenges existing models and encourages the development of better tools and theories. On a larger scale, studies like this reshape how we think about our place in the universe. The search is not only about finding life elsewhere, but also about understanding how common or rare life might be. Every new discovery adds another piece to a vast and still incomplete picture. Proxima b remains compelling not because of certainty, but because of possibility. Its unusual signals, complex environment, and proximity make it an ideal subject for continued exploration. Whether it ultimately reveals signs of life or simply deepens our knowledge of planetary science, it stands as a reminder that even the closest stars may hold mysteries we have yet to fully understand. And the deeper scientists look, the more the mystery seems to evolve rather than disappear. What initially appeared as faint, repeating infrared variations has now become part of a broader effort to understand how entire planetary systems behave under extreme conditions. Proxima b is no longer just a candidate for habitability. It has become a testing ground for the limits of our detection methods and our assumptions about life beyond Earth. One of the key challenges in studying such a distant world is separating signal from noise. At a distance of over 4 light-years, even the most advanced instruments are working at the edge of their capabilities. Tiny distortions from interstellar dust, interference from the host star, and limitations in sensor sensitivity all complicate the data. What looks like a clear pattern at first can sometimes dissolve under closer scrutiny. Yet, in this case, some elements of the signal have persisted across multiple observation cycles, keeping the question open. Researchers are now comparing these patterns against detailed planetary models. Simulations attempt to recreate Proxima b's environment under different conditions, varying atmospheric thickness, surface composition, and magnetic field strength. Some models suggest that if the planet has a dense atmosphere rich in greenhouse gases, heat could be redistributed from the star-facing side to the dark hemisphere. This could produce stable thermal gradients, which in turn might create repeating infrared signatures without requiring anything artificial. Other models explore the possibility of chemical cycles operating on a planetary scale. On Earth, seasonal changes drive predictable atmospheric shifts. On a tidally locked world, similar cycles could exist but follow entirely different rhythms, shaped by constant daylight on one side and permanent night on the other. These cycles might generate patterns that appear structured simply because they are governed by stable, repeating